This is Spencer Chin from Design News. I'm here with Ken O'Neill from AMD. We're going to talk about uh, what's been happening in outer space and some of the chip development and what role AMD has. So, Ken, uh, any opening thoughts on where chip development has been going as far as space development? Yeah.
Yeah, yeah. There's a couple of different areas where I think there's things I can say that might be interesting.
Mhm.
The first thing is that actually beyond space, having some degree of radiation mitigation has been part of the design philosophy that we have had in the embedded business group at AMD. We've had that for multiple generations, actually.
Mhm.
We see radiation issues terrestrially with a variety of different types of end systems, whether it's data center, carrier class telecommunications, automotive, aviation, and of course in space. So we have been motivated to mitigate the radiation effects that you experience as you go down into deeper and deeper submicron and nanometer scale semiconductors. We've been doing that for multiple generations, and that has lent itself very well to the deployment of our latest generation products in space. So when you talk about space as an environment, there's multiple reasons why space is a very hostile environment, and radiation is just one of them.
Mhm.
So the mitigation that we've done for multiple reasons, as I explained, in terms of radiation, that lends itself to space, but it doesn't address the thermal and mechanical issues that you have in space. So we
Right.
also, for our space grade parts, we also design packages that will withstand the very intense temperature cycles and the extreme temperatures that you experience in space that will withstand the shock and vibration of launch into space, and that also are tested and qualified following standards that were developed specifically for space electronics. So, so that's kind of where we are today with regard to the product portfolio that we offer for space flight applications.
Mhm. And I think one reason for this discussion has been there's been a lot of talk about AI. I know we've talked about, some of the hostile environments for chips in space, and that's something that AMD's been working on a long time. But
Mhm.
now this whole talk about AI, and on terrestrial applications, you have an issues there. What are some of how has chip development for space missions been affected by AI demands? I mean, uh, is this what impact has this had on AMD's chip development?
Oh,
Yeah.
for sure. So I can interpret your question two different ways.
Mhm.
To what degree is AI used in the development of the chips, and to what degree is the end use is AI the end use of the parts, and how has that influenced our
Yeah,
our
that's
parts?
fine.
So
Yeah, that would work.
I'll
Yeah,
actually
I mean that's kind of
address.
it does work both ways. Yeah.
Yeah,
Yeah.
yeah. So we obviously use AI in the development of our chips, our software, our solutions. I don't want to get into too much nitty-gritty detail because I'm frankly just not too sure how much I can say without starting to
Okay.
get into
Okay.
proprietary stuff about
Sure.
the tools
Mhm.
and techniques we use. But I
Mhm.
think it's safe to say that yes, AI is very much part of our development process for the products
Sure.
that we offer, products in the general sense, silicon as well as software.
Mhm.
Um, in terms of the in terms of the end use of the products in space, yes, AI is definitely a growing area of application for our devices in space, and we see it across a spectrum. AI is a very, very general term applies to so many different things.
Sure.
But in space and with many other markets, there's kind of a crawl, walk, run kind of growth path for the use of AI, and some of the early uses of AI that we've seen in space, I would consider to be very localized inferencing types of
Okay. Hmm.
applications. So I can give you a few examples
Sure.
there. One example would be in an optical imaging satellite application. If you're doing remote sensing and doing visual imaging of the surface of the Earth. Well, the Earth is covered in cloud.
Hmm.
Roughly 60% of the surface of the Earth is covered in cloud at any point in time. And if what you're actually hoping to capture images of is the surface of the ocean or the surface of the land, well, 60% of your images are going to contain clouds and not show you the things you want to see.
Hmm.
So you can waste a lot of storage space, you can waste a lot of power doing processing, and you can waste a lot of downlink bandwidth
Hmm.
by sending images of the tops of clouds. And so having cloud detection is an AI-based application that can save power, um, prolong the lifetime of the satellite, and minimize the use of downlink bandwidth just by detecting pixels within frames that
Hmm.
have clouds in them and don't contain useful information. So cloud detection is an example. There's
Hmm.
been a lot of work being done by multiple organizations on multiple continents around the world on wildfire detection. So
Hmm.
again, using AI to detect wildfires
Hmm.
quicker than you can detect them on the ground, particularly in remote
Hmm.
locations. Um, so from space, you can get early warning of
Hmm.
emerging wildfires and take remedial action against those. Again, it's
Hmm.
based around um, AI inferencing on sensor data
Hmm.
um, that it's a little different to the classical optical image recognition and classification because a wildfire isn't necessarily a particular shape. You're not
Hmm.
recognizing shapes here. You're recognizing IR signatures and you're recognizing the impact uh, that wildfire has on vegetation, which you can detect through infrared imaging, but you can also detect through radio frequency imaging from radar as well. So it's quite a different application to just the traditional uh, image recognition types of things. And then the final example I wanted to give you relates to spacecraft health data itself.
Hmm.
So satellites have many different telemetry channels on board, monitoring voltage and current, temperature, mechanical stresses and strains, magnetic field, pressure, flow rate, things like that. All of that information is gathered and is collected and transmitted to the Earth because it can be indicative of an impending failure of a system on board the satellite.
Hmm.
And if you're armed with that telemetry data and you do detect that there's an impending failure of an instrument or a system on board a satellite, then it allows you to take early remedial action, which could be, hey, maybe our system is getting too hot too fast, so we need to throttle back how we're using it or use it only for the most essential parts of the mission, or our satellite is really on a path to failure
Hmm.
and we're in a constellation, we have orbiting spares, we need to move an orbiting spare out of the spares orbit and into the active orbit to take over for the satellite that's failing. before we have a loss of revenue or a loss of mission. Um, so we actually have a reference design for the telemetry anomaly detection using
Hmm.
recurrent neural networks. So those are examples of little local solutions. And if you go out to the other end of the scale, there's a lot of talk about data centers in space. So
Right.
the whole idea there, of course, is not individual localized point inferencing of AI solutions. It's about training very large AI
Okay.
models.
So
It
before we get into that, yeah, I just want to get into that in a couple of minutes. Just to
Oh, sure,
backtrack
yeah,
on this on some of the local applications you mentioned.
yeah.
So in as far as like talk about wildlife detection. So you're saying that traditional optical recognition, it's only recognize is traditional optical recognition only recognizing shapes, or is it recognizing the IR's is it actually recognizing the IR's signature image, or is it only the visual image of the of say a wildfire.
Well,
Yeah.
so I'm thinking, okay, if you have something like YOLO, which is identifying shapes of things,
Hmm.
because it's been trained on labeled images, cats, dogs, bicycles, whatever it happens to be.
Hmm.
But wildfire is not there's not a standard shape for a
Hmm.
wildfire. A wildfire, the signature of a wildfire is its infrared signature
Okay.
and and its uh, and its effect on vegetation. So as I mentioned, radar actually is a useful mechanism for detecting wildfires because um, if the leaves are burned off the trees, then the trees reflect radar in a
All
way
right.
that's completely different to how they have how it
Okay.
would if they have leaves on
Great.
them.
Okay. And as far as the telemetry data, you're saying that uh, so this telemetry data you can actually send another satellite into space. You said you have like a reference design for what is that for a satellite for a some kind of processing circuitry.
No, it's the reference design is actually it's a design that actually runs in the AI engines on
Okay.
board one of our smallest space grade FPGAs today.
Mm-hmm.
It's a very compact little design. And you can host it like you may have one of these devices in your system already. And if you have some spare capacity in that device, you can actually put this recurrent neural network design in there to do the detection of anomalies in the telemetry data.
Mm-hmm. I got it. Okay. So let's see. That's great. Uh, then you kind of talked about data centers. I mean, uh, what's the push, right? Uh, what would the advantage of a what do you see as the advantage of, say, putting a data center in outer space? And would these data centers just be for satellites, or would it be an earthbound, some kind of earthbound data center that happens to be in outer space? Or would it be a specialized data center for, say, satellite data? Yeah.
Yeah, all of the above.
Okay.
So, yeah, I can give you some examples.
Sure.
So let's say, for the sake of argument, you have a deep space mission or a lunar mission. You know, the communications latency back to Earth is really problematic.
Mm.
So if you want to have intense processing, heavy
Right.
duty processing of sensor data that's being gathered in the deep space mission or the lunar mission, then it makes sense to have the processing capability local to where the data is being collected.
Hmm.
So that would kind of point towards data centers that would be either in lunar orbit or maybe even on the surface of the moon, although I will say that being on the surface of the moon is really a challenging, difficult environment for a data center. If I was building a lunar data center, I'd put it in orbit and
Right.
not on the surface. And the reason for that is um, the surface of the moon has very extreme temperature variations. So
Right.
a lunar day is actually, the cycle between sunlight and nighttime on the moon is actually 29 days.
Hmm.
So it's exposed to bright sunlight for 14 and a half days and then no exposure to sunlight for 14 and a half days. That's a
Hmm.
big thermal challenge.
Right.
It's also a power generation challenge because if you're using solar cells to generate the power, you're going to have to go 14 and a half days with no solar power. So you need
Hmm.
a lot of battery backup to power any electronics on the moon for the long lunar night. Um, so much better to actually fly it in orbit where
Right.
you can have more constant illumination.
Hmm.
But that's just one class of data center. Um, Not to trivialize the amount of compute that would be needed there, but those are not, in my mind, those are not the biggest, most heavy duty compute types of data center that could be flown in space. So terrestrially, we're talking about, they're building data centers in the multiple hundreds of megawatts
Right.
today, and there's around the world there's plans for gigawatt class data centers. The problem that we have in the U.S. Is that planning permission takes a
Right.
long time to get planning permission to build a terrestrial data center. The power infrastructure is difficult to create. And there's also political and
Right.
regulatory issues. Like there's something like 30 states have expressed either an outright ban on constructing data centers or have expressed significant reluctance to host any more data centers in their state. Um, the problem is if we do that universally across the whole of the country, then you know new data centers being created are going to be created um, potentially dominated by adversary countries, and
Right.
that's not good for national security at
Sure.
all.
Sure.
So that's one incentive for putting data centers into space. Get around the regulatory and the power limitations. There's also some security aspects to that. It's an awful lot harder to mount a physical attack on a data center if it's hundreds of kilometers in the sky.
Hmm.
Um, so the economics of it and the engineering challenges are absolutely non-trivial. So it's not going to be an easy thing, but in some cases, the ability to avoid the regulatory issues and and the power generation issues may make it worthwhile to put data centers in space. And there's um, I don't know how many, at least a dozen, maybe several dozen organizations, from small startup companies
Right.
to much, much larger companies um, who are currently working on um, prototyping and doing some Pathfinder work at putting uh, data center type compute resources into space
Hmm.
as Pathfinder missions. Kilowatt class things, not megawatt or gigawatt today, but ultimately to do fact finding
Hmm.
in service of getting to a point where they put data centers that are hundreds of megawatts or gigawatts into space.
So right now, uh, there's actually some exploratory work on, I guess, like these like feasibility missions to see whether a data center can be done in outer space, and then
Hmm.
yeah. So are these efforts, these companies that are doing it, are they U.S. companies or international companies? Are they joint efforts between the U.S. and other countries, or are these from other companies in other countries, or what?
Yeah, it's all over. There are US based startups that are operating with venture capital to launch Pathfinder missions. There's international companies,
Hmm.
European companies, Asian companies as well,
Hmm.
and then some larger companies have all talked about having data center
Hmm.
capabilities in space. SpaceX, for example, um, Blue Origin as well, um, and others.
Hmm.
Uh,
So this being the case that they're starting to do work on some of these exploratory missions, what would
mhm.
that mean to say a chip company like AI? I mean, are there potential discussions with you and maybe other chip companies to develop say GPUs and CPUs that can not only handle the amount of data but also withstand the harsh environment of outer space? In
Mhm.
other words, you would have to make the chip robust enough to withstand radiation as well as the thermal and other harsh aspects of being in outer space.
Yeah, so we're very much in the early phases of exploring what'll be required to be successful with data centers in space. We are talking to a number of companies who are active in that field with the intent of determining, okay, how much radiation hardening is needed for a
Mm,
GPU in space to be functional, to be useful, and also what kind of mechanical properties are needed to withstand launch and to withstand the thermal and mechanical stresses of
mhm,
operating in space. Um, so definitely very much on the exploratory side. It's we're at the beginning of this
mm.
journey today. But I did want to mention a couple of things
Sure.
that might be interesting. Um, so the compute resources, of course, are the whole reason to put data centers into space. Um, but when you think about what it would take to actually have a large number of GPUs in space operating together as a coherent data
Mm,
center, you'll realize that there's pretty significant communications challenges that have to be overcome. There's thermal and power generation challenges that need to be overcome, and of course there's radiation challenges. My own belief on this is that the engineering challenges to be overcome are immense.
mhm,
They are truly huge. But I also know that there's some extremely smart people working
mhm,
on these problems, um, and also some extremely well-funded people.
mhm.
So smart people who are well-funded have a habit of coming up with
Right,
successful solutions. So the engineering challenges, while they may be immense,
right.
I don't believe they're impossible.
So, I
And
mean, basically, uh, I think it sounds like people realize the effort it will take to do it, and uh, companies and maybe even agencies could hopefully obtain the funding in order to do this development.
mhm,
Uh, yeah, uh,
yeah,
yeah.
and I
Although
think
in the U.S. though, I mean, with the cut of NASA, I don't know, that may be a little bit more of a challenge going forward. That they've cut, as you know, they've cut the budget in NASA over the past few years, and
mm,
it's kind of. Although I think Trump wants to promote AI, so uh, he might be open to this.
yeah, yeah. I mean, there's money uh, from government sources. There's
Mhm,
private venture money, and there's money that's coming from large corporations. So the funding is coming from multiple directions, and I think the thing here is to get some early success and some
Right.
early learning. The approaches that we're seeing from multiple companies who are active in this field is to totally reimagine what a data center is,
Hmm.
because a traditional terrestrial data center is essentially a three-dimensional structure where you've
Right.
got layers of server boards in a
Sure.
rack. The rack expands in two directions,
Right.
um, left and right, and also there are multiple rows of these things. So you have essentially a three-dimensional structure with an array, three-dimensional array of GPUs, all
Hmm.
intercommunicating and their activities being orchestrated. In space, I think it has to be different,
Right.
um, because you know that terrestrial structure works where you're able to cool things with forced air, with air conditioning and forced air. You cannot do that in space.
Right.
So I imagine a more two-dimensional structure for
Hmm.
space, where you've got solar panels on one side, thermal radiators on the other side, and the GPUs sandwiched in between.
Hmm.
And that's all well and good. That's thermally efficient. It takes care of the
Right.
power generation and the thermal effects. But now your communication between GPUs is in two dimensions, not in three dimensions. Um, so that ultimately may end up being a limiting factor, uh, because doing a machine learning training exercise relies on very fast communication between GPUs. If you inject too much communication latency between GPUs, then your ML, your machine learning training exercise just bogs down and doesn't happen
Hmm.
um, correctly.
You would have to make such a structure, though. In outer space, on Earth, you can make a data center. All these data centers, these concepts for data centers, these physical data centers you've seen pictures of, they're all like vast. And that's part of the problem because companies don't want these big structures in the backyard. In outer
Yeah.
space, you may not, you have plenty of room, but you also got to keep the weight down. You got to
Yeah.
keep the weight down of these things, while at the same time giving the thermal and radiation protection. So, uh, that's before you go into the communications. Trying to. So you're talking about engineering something that has to be, uh, light, light, but without losing its robustness as far as handling thermal, and radiation and all that.
Hmm.
So that sounds like it's, a significant challenge. That's even before, as you say, how do you communicate? I don't know, maybe there's some kind of, maybe it's some optical. There's a lot of talk about optical communication now.
Hmm.
Maybe if you can achieve optical communications out of space. Uh,
Yeah.
yeah.
Yeah, for sure. So you hit the nail on the head actually with weight or
Hmm.
mass. So thermal solutions add significantly
Right.
to the mass of a satellite because the thermal radiators are not light, and you need metal structures to conduct heat away from electronics that are generating heat.
Hmm.
And mass equals launch cost.
Right.
Um, so the economics of data centers in space, um, the economics are another area that there needs to be, um, how should I say it? There needs to be further development. So the viability of some of the uh, multi-megawatt and gigawatt class data center structures that are being talked about at the moment, I mean, they really do depend on launch costs continuing to decline dramatically,
Hmm.
um, so that you can have multiple launches, with each launch launching multiple compute modules
Right.
uh, at modest cost per kilogram.
Mm-hmm.
Um, and I mean, the way I kind of see it playing out is with modular compute resources that get launched, um, many at a time, but there needs to be many launches. And then these modular compute resources kind of autonomously self-assemble into an array, where they communicate with each other and do their own health monitoring. And if one of them has a radiation, a destructive radiation effect,
Mm-hmm.
it self monitors and takes itself out of the array and deorbits itself, and at the same time sends a signal to queue up another module to come in and replace it.
Mm-hmm.
So, um, we were talking about AI, and you need AI to do that kind of self-monitoring and autonomous self-assembly and autonomous disassembly. Um, so while the intent of the data center in space is to facilitate further use of AI by humanity, by
Mm-hmm.
helping to train large models,
Mm-hmm.
you need AI in the data center to make it work,
Right.
to keep
So
it.
that brings up an interesting point, though. A
Mm,
lot of the development has been in generative AI, and now there's work. Do you see agentic AI and physical AI entering the equation? For, do you see agentic
yeah.
AI entering the equation here? Because that would, I guess, be an agent. It would learn and teach, and uh, is that going to play a much more important role in outer space then? Uh,
Yeah, I think there's potential for that. I
mm,
mean, if you can imagine an array of literally thousands or maybe even tens of thousands of compute modules where, if you equip those compute modules with agentic AI, um, and physical AI too, depending on where the boundary of definition
right.
of physical AI begins and ends. But let's say each one of those modules is equipped with agentic AI and with physical AI, then they can learn the most effective ways to self-assemble and
Right.
disassemble. They can learn to recognize indications of impending end of life, at a module level, and learn to recognize when they need to take themselves out of service um, before anything calamitous happens to the
Hmm.
entire array. Um, and then the physical AI part of it, um, mm, maybe it's a maybe for me, and the
Right.
reason I
Right.
say that is because the self-assembly and self-disassembly, you may be able to do that relatively effectively without getting into physical AI. There's companies at the moment that are proposing to have the
Hmm.
self-assembly and disassembly capability using magnetics
Hmm.
to move compute modules into the right
Hmm.
place. Um, if the magnetics are controlled by AI, does that extend into the realm of physical AI?
Right.
I don't know.
Yeah.
Maybe.
But
Depends
AI
where
would be
you.
involved. I mean, whatever the
Yeah,
classification is, you're saying that AI would be involved, then it would still be involved, whatever form you want to, and
yeah, yeah.
yeah, without trying to get into fine detail of where you classify it. I mean, it's going to play a role. It's going to play a role in how these things operate. I mean,
Right. Yeah, I certainly think there's definitely a role for physical AI in some of the exploration programs, totally outside of the data center conversation, but lunar exploration, deep space exploration, having physical AI, as a way of speeding up and making more effective our work at exploring. the moon,
Mm,
other planets, the moons of other planets, and then potentially also having physical AI as a mechanism to help clean up low Earth orbit. So
mm,
um, the amount of debris that exists in low Earth orbit at the moment is um, it's a significant impending problem. There's already been collisions of of satellites. I
right,
guess it's quite a few years ago now. There was a non-functional, uncontrollable. I think it was a Russian satellite, but I wouldn't swear to it being
right,
Russian. I think it was Russian. Collided with an operating communication satellite, and I think it was one of the Iridium Next satellites. Create a huge debris field. And of course, the more debris you have, the more probability there are for more collisions
mm,
and even more debris. So it's an exponential kind of a problem. So can physical AI be used um, to retrieve and deorbit some of the debris that's potentially being problematic out there in low Earth
mm.
orbit? I think that's a really interesting
Interesting.
area for future research.
So you're
Well, it's not
envisioning
future, it's
maybe,
current.
yeah. So you're envisioning maybe robots. I mean, constructing robots that can actually retrieve some of the space debris. I
Hmm.
mean, would that be the idea you have, or what? Yeah.
Yeah, yeah,
Okay.
it's not so far-fetched actually.
Hmm.
There are
No, it's not.
programs today.
Mm,
Yeah, there's a program. If you go on YouTube, there's a company in Japan that has their mission is to retrieve. I think it's the second stage of an H-2A launch vehicle. So this is not a small piece of debris. It's
mm,
the upper stage of a rocket, um, and they've already successfully launched a spacecraft out there into low Earth orbit, and that spacecraft has actually orbited the the disused launch vehicle
mm,
and sent back images of it from space. So it's been out there. Both things are orbiting the Earth, and as they're both orbiting the Earth, this smaller spacecraft is orbiting the debris.
mm,
Because phase one of their mission is go up, get photographs.
mm,
Phase two of the mission is go up, attach to it, and then deorbit it, bring
mm.
it bring it down.
Yeah. Um, Ken, I want to address, obviously one of the issues today in general has been the reliability, reliability of the data, reliability of the algorithms and all that. How do you, being that we're talking about very critical missions, you're spending a lot of money, it's a lot of money invested in these aircraft, a lot of money, there's a lot of security considerations. How do you better deal with some of these potential security problems? Uh, or how do you make, some of these systems, uh, uh, how can the AI be more, I guess, reliable and secure in outer space, which is going to be critical? Yeah.
Hmm. Yeah, so there's that's a multi-layer
Mm,
answer actually. So um, secure communications from ground to data center to ground, and between data center compute elements. So security is an important topic that we address. I'm not the expert. If you
right.
if you did want a deeper dive into
Mm,
security with people who
mm,
could do it better than I can, but each generation of device that we offer has upgraded security. Our latest parts have post-quantum crypto capable secure features on board. Um, so communication security is definitely a factor there
mm,
to make sure that um, your data streams into and out of are not
mm,
being hacked or tampered with. Having secure boot capability so that um, when a system is coming online, and it is powering itself up, there needs to be a root of trust.
Right.
So um, there needs to be a function within that system that authenticates itself and authenticates everything that is used to bring the system up, so that if there is any attempt to subvert the function of the equipment by hacking
Hmm.
the boot code of the processors, for example, or something like that, then there needs to be a system that authenticates the boot code of the processors or authenticates the software that the processors are running on,
Right.
to make sure that it is truly the right software.
Hmm.
So we have solutions that overcome a variety of different attack vectors.
Hmm.
Um, and yeah, I should probably stop at that point because I'm not the not the security
No, I
guy.
don't need to know I mean, the
Yeah.
details obviously is that's another level of discussion which we don't need to get into. But
Mhm.
I, I think what you're saying though is pretty much a solution. It's pretty much it though. You have to really authenticate within the hardware. It's not something that you can rely on software. You got to authenticate within in the boot code. You have to encrypt as
Exactly.
much security as yeah.
Yeah.
That is the approach. And
Yeah.
that probably goes beyond, current that probably goes way beyond, all these current standards that are mandated by, say, NIST and then, these other agencies. It would
Mhm.
probably have to be uh, much more secure than that because, yeah,
Yeah.
yeah.
I think the key word there is hardware root of trust.
Hmm.
Because, like you said, you cannot rely on software to do this. You need a hardware root of
Right.
trust.
Hmm. Okay. Uh, and as far as the ensuring the reliability of the AI, though, I mean, uh, I imagine though you would have to accumulate enough data. I mean, the AI would have to. I guess the issue here would be trying to accumulate enough data to determine how reliable it is. But then the AI would have to uh, be able to learn it and apply it in the future. But I guess the question is, how do you know? I mean, without the knowledge base just being established, uh, how much of that knowledge base has to be built up before you can rely on that AI within the knowledge base to uh, govern everything or to help,
Hmm.
govern everything. Yeah.
Yeah. Again, it's kind of a big question.
Hmm.
So uh, there's a couple of different directions I wanted to go at with this
Sure.
one. Number one is for local AI inferencing. Um, we certainly have experience uh, where AI inferencing, certain types of AI inferencing. So I don't think I can say this universally,
Right.
but it is true that certain types of AI inferencing are relatively tolerant to um, uh, to upsets
Uh-huh.
in the AI hardware.
Hmm.
So I'm thinking, when I say that, I'm thinking really about a radiation environment. So, I don't want I don't want to make a claim that that's universally true,
Right.
but in a device that's being deployed in space, a modest amount of radiation upsets in a convolutional neural network does not deteriorate the results of the network too dramatically.
Hmm.
Um, Now we have seen evidence from some of our own testing actually that as you expose a convolutional neural network, and we're thinking image processing here,
Hmm.
as you expose it to radiation, you are going to get a degradation. Um, the first and least severe form of degradation is that the AI does correctly identify um, the image,
Right.
correctly classifies, but its probability or its how it assesses the certainty of its decision decreases. So it may identify the object correctly, but it says I'm only 70% confident that I've identified it correctly.
Mm-hmm.
Whereas without radiation, it would be saying I'm 95% confident
Mm-hmm.
I've identified it correctly. So that's one effect that we observe. The other effect that we observe with more severe radiation is that it just misidentifies what it's looking at, and we do see that. Um, what we have experimented with is actually fault-aware training,
Mm-hmm.
meaning that instead of just training the AI model on, I guess, pristine images,
Right.
labeled images, we actually train the AI on noisy images,
Uh-huh.
that
Right.
faulty images. And by doing that, we were actually able to dramatically improve the accuracy and
Mm-hmm.
the accuracy of classification and also the certainty of classification by something like a factor of four,
Mm-hmm.
something like that. I'm struggling to remember the exact numbers, but let's just say that significant improvements um, in inferencing can be achieved with fault-aware training
Mm-hmm.
in the case of image classification.
So photo-aware training, that's something that is that something that is well understood? Is that something that how difficult is something like that to deploy though? Because you could have you could have so much there's going to be so much variations in data and observed images and all that. Uh, would that be a very difficult, could that be potentially a difficult thing to train for, or would it really depend on the classification of the fault and the
Yeah, I
type of
don't
fault?
know.
Yeah.
I don't know. I'm
Mm,
not sure how to answer that because
yeah.
it's, it's outside my expertise, and
Sure.
also
Mm,
it's kind of out of scope for us.
mm,
We provide the platform, the
right.
platform for the training and the inferencing. But generally speaking, we see that customers who are deploying AI inferencing in space are going to not use off-the-shelf models. They're going to go and do their own
Okay.
training,
Mhm.
and so yeah, I'm sorry, I just don't know how to
No,
answer that.
that's a good
Yeah,
point though. No, that's a
yeah,
very good point because I can't see. That's what I'm trying to get at. Uh, I don't think, existing off-the-shelf models can apply in space because you don't have that specialized data, or you don't have that
yeah.
specialized set of parameters and all that. You have to sort of you have to sort of develop it by experience, but it's not gonna it's kind of I imagine it would be kind of a gradual buildup because uh, you're deploying these things in stages probably. You're not gonna uh, build up
Hmm.
the database so much already unless you have experience in it. So I think what
Hmm.
you're saying is that the customer would have to develop its own solution, but at the same time learn and train from that information. Yeah.
Yeah, it depends what it is we're talking
Mm-hmm.
about. I mean, I can imagine some types of applications. Let's say you're doing a land use mission,
Mm-hmm.
and your objective is to look at how land is being used, what type of crops are being grown, um, uh, y you know, across the world. Let's say you're looking at South America, Africa, India. You're flying around in low Earth orbit doing that. So the amount of data that already exists on the hyperspectral imaging properties or the hyperspectral properties of different types of crops or different types of vegetation is probably very well known.
Mm-hmm.
So training an AI model on that probably is um, fairly routine. I'm not going to
Mm-hmm.
say trivial or
Right.
straightforward because I don't think any of it's trivial or straightforward. But is it routine? Yeah, probably. In that it's not like you know first principles new
Right.
science or something like
Sure.
that.
Mm.
I think the problem is that we have in space you can have situations where you're looking at things that either have not been looked at before or things that have not been looked at in the level of detail that you want to look at them
Hmm.
before. And therefore, there isn't a pre-existing trained AI data set.
Right.
Um, so, yeah, it
Yeah.
all depends what your mission is. Science
Great.
mission might be easier than a defense mission, or a commercial mission for that matter. So,
Now, interesting you mentioned defense there. I imagine that's probably what some people are thinking, though. Would that be would that be a challenge, though, as far as trying to use AI for defense? I mean, uh, aside from the obvious security issues, but would that be a very difficult thing to train for? Because you may not be aware of of what some of these other potential dangers are.
mhm.
Yeah, yeah,
Yeah, I think the problem with AI in defense systems, one issue with AI in defense systems uh, is that the available data for training is limited,
right,
and it's in the best interest of any adversary to to move quickly in deploying
right,
new capabilities. So this is not just a space discussion. This is a general
right,
um, defense discussion. But let's say that um, you are in some kind of a communications application,
hmm,
um, and your intent is to identify enemy communications.
right,
Um, and you might think, hey, I can use AI to do that, but your enemy is deploying new waveforms and new modulation techniques rapidly,
right.
um, and so you don't have the training data to create um, the AI models for
And
inferencing.
you're adding to that the additional complexities of being operating out of space, on top of the usual defense,
Hmm.
usual defense issues, because as you say, the adversaries are moving quickly. They're going to be as much stealth as possible.
Yeah,
You add the outer space layer to that, that's going to be, yeah, that becomes very difficult.
yeah.
Yeah, problem. Okay.